everyone. Last video we talked about polynomials, and I just sort of said, hey, you can distribute derivatives across plus and minus signs and pull out constants because it's linear. Let's go ahead and take a second and do that properly. So derivatives have this nice sum property as an addition, which means that if you see two things added together, then to take the derivative, I just do them separately and keep that addition sign. Same with subtraction, very nice. So that addition is just going to turn into a subtraction. And if there is a constant multiple in the front, then that constant multiple just hangs out. Okay, this is unreasonably nice. This is not the case in most situations, right? I cannot just pull out the number 5 from a natural log or a square root. There are usually complicated rules. The fact that I get to do this with derivatives is more than I could hope for, this linearity. It also means you need to be really careful about what is a variable and what is a constant, because x squared is very, very different from 2 to the x. So 2 to the x we don't know how to do yet. Just to show you why this works, let's take a quick second here and maybe half prove one or two of them. So let's do the constant multiple one first. Let's just go ahead and consider the function c f of x. Okay, so this new constant multiplier. Well, my definition says that the derivative of this thing is just going to be c f of x plus h minus c f of x all over h. Now I've got this c out front of both of these, and I can factor that out entirely. I can pull it all the way out of the fraction. But my limit law says I can also pull a constant all the way out of the limit. And so this becomes c times the limit as h goes to 0 of f of x plus h minus f of x all over h. Neat. I was able to pull that c all the way out of the limit, and now I know what this thing is. This should look very, very, very familiar to you. The c is going to hang out, and this just becomes f prime of x. That is the definition of my derivative. So nice. All right. We could, if we wanted to, play the same game with f plus g. I encourage you to do that. And in this case, you can actually split your limit up into two different limits, which is very nice, again, using our limit laws. So same kind of a process for the sum and the differences. I think I'm just going to do the one for now. Okay, but the point here is that this linearity of the derivative, one, is super nice. 2 means you have to keep track of what is a constant and what is a variable. 3 comes right from our limit laws. Because I can split up across plus signs for the derivative, or for the limit, I can do it with this derivative function. And because I can pull out a constant in the limit, I can do it for the derivative. Right? It's not just some nice pattern you copy, it's one that you understand. Okay, next up, while we're talking about how nice this derivative function is, it's worth asking yourself, what is the nicest derivative I could possibly think of? What is the nicest function or behavior I could ever want? And usually at this point, people will say something like a constant, right? If I take the derivative of a constant, I get 0, and that is definitely nice. Okay? Or they might even say, hey, if I take the derivative of x, I get 1, and that is also definitely nice. Okay, but there's some other really nice behavior I might want to try to find, right? I might, if I had some function y, and I took its derivative, what is the nicest thing that could come out other than maybe 0, which is nice? Well, I would argue y. Taking the derivative does nothing. It returns the same function. That is a pretty nice behavior, and that would be something you would want to put a little mental note for when does this happen. This, by the way, is an example of a differential equation. It is an equation with derivatives in it. And the function that satisfies this is a solution to this differential equation. Now, this is a Calculus 1 class. We don't need to worry too much about differential equations, but it's good to know that you're secretly solving them and using them all the while. So there is a function that satisfies this. It's one that maybe seemed mysterious up to this point. It is our old friend e to the x. E to the x, this thing, why did they make me learn so much about it? It turns out it shows up everywhere. And one of the reasons it shows up everywhere is because it's its own derivative. It's its own derivative. So let's think about that for just a second. Here's me quickly sketching e to the x, which I hope you can sketch too pretty quickly. What this is saying is that when I am at 0, e to the x is 1, and the slope, if I drew this right, it's not to scale, the slope should also be 1. And when I'm at e squared, the slope is also e squared. Its height is actually telling you exactly how fast it is growing. That's pretty remarkable. That's a pretty neat thing. It also means that taking its derivative is really, really easy. Let's give this a try. So 3e to the x, we just learned this constant rule. That 3 is going to hang out. The derivative of e to the x is just e to the x. Plus e squared, don't be fooled, e squared is a constant. So the derivative of a constant is a 0. If there's not an x up there, it is not an exponential function, just a constant. And then this is just our old friend, 5 times 3x squared. If we clean all this up, we get 3e to the x plus 15x squared. Very nice. So there isn't that much to do in terms of examples for this one because they all look the same. The derivative of e to the x is e to the x. We still need to figure out what 2 to the x is, and we still need to prove this. The proof is also pretty darn neat, but I'm going to put it off until a later video so that we can get some practice in on these techniques. So a couple of more examples in this realm of things that might catch you on the fly. How could you do these two examples below? Worth thinking about. So the trick here is that often you need to do algebra. Often a little bit of simplification will go a long way into making your life better. Even when you know other ways of doing something like this, like the quotient rule, algebra is the right way to do this. So let's just rewrite this as 4 over x plus x squared over x. The numerator distributes, the denominator does not. So I can do this with a numerator, and now this looks a lot better. This looks like 4x to the negative 1 plus x. And that is super easy. This is just negative 4x to the negative 2. Notice I'm going a bit faster now, plus 1. Okay, so a little bit of algebra, splitting up those numerators can help you out a lot. Here, oh man, I don't know what to do with that squared because this is not x squared, this is x minus 3 squared. But I do know how to FOIL that out, so this becomes x squared minus 6x plus 9. So when taking derivatives, expanding things out is often your friend. Finishing this up, we get 2x minus 6 plus 0. I'm going to leave it just like that. Very nice, very nice. Maybe a quick warning here. There is still lots of stuff we don't know how to do. In particular, something like x e to the x. These two functions are multiplying each other. I don't know what to do about that. I don't know what to do about e to the 2x. Okay, this is why we had to do a little bit of algebra before on these things, right? Was to get them into a place where they looked more linear, right? More spread out into different terms that we knew how to work with. So algebra is your friend, but also knowing your limits is your friend. We will be able to do these kinds of things in the future. I also still don't know what 2 to the x is. Not equals, I guess. The derivative. Okay, and we'll get to all of those later in this class, give you something to look forward to. Okay, everything in this section is crucial. Everything in this section is going to come up a lot. So practice, practice, practice.